All right, folks. Welcome back to your last class together. And for some of you, your last class ever. A few of you can nod at that, right? Yeah, it feels good, I imagine. It's a period of transition. So as I announced in class on Tuesday, and as I sent out an email yesterday, course evaluations. So here's where you're at. This class is 15 out of 20, and I said everybody gets a bonus point of extra credit if you get 18 out of 20. So I don't know who has responded and who hasn't, but I can send out a reminder to the people who haven't tomorrow as another chance to highlight that opportunity. I believe they close Sunday this year instead of Saturday, so you can work on it over the weekend. The other one that I offered was a Qualtrics survey, which you all should have received an email invitation to complete. If you need me to resend an invitation, I can do so, just let me know. That one is open until the end of finals week, and you each get a point of extra credit if you're willing to complete that. For those of you who are concerned that this practice is somehow biasing my course evaluations, let me be crystal clear. I'm not giving you extra credit to give me good evaluations. I'm giving you extra credit to give an evaluation. If you'd like to take the point and nuke me, that is well within your rights. I will tell you that the quantitative numbers are used for things like merit review and raises and in junior faculty promotion and tenure. But if you give me a 1 out of 5 on something, that's not very helpful to me to figure out how I could have done better. So in this instance, I am much more of a qualitative researcher in that I want your feedback about specific elements, good things, bad things. In particular, in this class, I tried to do some different things. So more written exercises, the projects, the presentations, the ChatGPT thing. So this is my first try at this. So let me know what you thought of this. And if you have suggestions as to how to make those activities more useful, then certainly I'm all ears to that. So I value your feedback, and I want to compensate you for providing careful feedback, which is the basis of the opportunity for extra credit. Fair? Okay. Just to make that clear. So we will see how the other class does. Right now they have a little bit of a margin on you, but there's more of them. So we're going with percentages. Otherwise, let's see. Only one thing left to do. I updated grades this morning. So all of your project-related points are under the homework tally. You can log into the homework system and see how you stand with respect to points earned. The only thing that is outstanding is the last homework is worth 17 points. Again, if you want to provide a draft of that for preliminary feedback, then you are welcome to do so by tomorrow night. It doesn't have to be a complete draft. So if you only have time to answer a couple questions and you'd like feedback on those, I'm fine with that. It's an informal process. For better or worse, the final version, though, has to be in by the end of finals week. And I do not give incompletes. So if you're thinking about that, don't. Incompletes are not your friend. They're not my friend, because the farther you get away from this material, the harder it is to come back to it and figure out what's going on. So plan to get everything done by the end of next week. To help you get everything done by the end of next week, if you need some extra feedback or time with me, I have office hours Monday and Wednesday from 12 to 1:30 as usual. I am also holding extra office hours during the time I would normally be teaching, Tuesday, Thursday, from 12:30 to 3:30. So that is, trying to do the math here, 9 hours of office hours next week for anybody who wants to come talk to me. And if you want to talk to me about other things besides class stuff, then that's fair game too. So I'll just be sitting on Zoom, hanging out, waiting for folks to stop by. Let's see. We have a little bit of stuff left to cover. We'll see how much we get through. I thought it might be useful to try, rather than going back over what we covered before and review in the same form, to try it in a different form with some numbers, maybe an example of 3-level models and partitioning variance. Does that sound like a reasonable suggestion? Okay. Anything I'm forgetting or that you want to ask me about before we jump back in? All right, then away we go. So the context of this is longitudinal twin data. This is the octo-twin data set in yet another form. So I have about 100 different versions of this data set across all of my examples, selected for certain reasons. The one that I'm going with right here is 4 occasions, because the last occasion is mostly missing data. Approximately every 2 years, This example features 340 incomplete same-sex twin pairs. So they're either MZ or DZ, but they're all same-sex, and 615 people, and a total of 1,622 observations. So this is an unbalanced, incomplete type of data set. As you would imagine, twins probably have some commonality to their outcome. And in fact, that is the entire point of a sampling design that features people who are genetically related, is usually to try to decompose how much of the variability is common to the family due to genetic factors versus external factors versus error and all that kind of stuff. So we're going to be examining change over time. So this is just an unconditional set of models with respect to what we're building up to, just time, because that's enough. This is already a 13-page handout, and all I have is time. There are other versions of this handout that include a time-varying predictor. An earlier version I note from 2013, I gave a workshop at the University of Kentucky, and I also included SPSS in those materials. So if you want to learn how to do this in SPSS, I would direct you to my workshop page. Generally speaking, I keep all of my archive stuff online because at workshops I tend to do whatever software package people want, and so sometimes there's different combinations of what I have available. So we are looking at a measure of, outcome measure is a measure of cognition, but it's the information test, which is a measure of crystallized intelligence. So this is just like facts about the world that people should know. It's not something that should change as people get older, except in the instance of pathology. So this is not like processing speed or working memory or things that would typically show age-related decline. That's going to be important in considering this. Can I share my screen? Why, yes, I
can. Thank you.
Don't believe me? Just watch. Thank you, Jacinta. There we go. So yes, I hadn't gotten very far, though. I'm still just talking about the intro paragraph. This is example 6. So I've got Stata in R, and I have 2 of the models NM+ inside the download packet just for completeness. So nothing new here with respect to making new variables. The logic by which I've made these variables I want to discuss subsequently. So I'm going to skip this part for right now. So first things first, empty means 2-level model for cognition. So in this notation, quit it word, I want lowercase I. It never lets me keep lowercase I as a subscript. So I have T for time and I for individual, and here's my little empty model predicting information test. So just 2 different variance components here, a level 1 residual, which is variation over time within a person, and a level 2 random intercept, which is between person differences as usual. So nothing of note really about the code here. We're using REML, Satterthwaite degrees of freedom, so the results from M+ will differ slightly because of the use of ML instead. And I have in these 2 codes here a variable that is called case. This variable is a unique person identifier, so it's just like an index of person that does not keep track of which family they're from. So I needed that because of the way that the code works in both of these packages. We're going to switch to a different ID variable when we differentiate which family the twins come from. So fixed intercept, random intercept, we're asking for an interclass correlation as well as a test of it. So I only have the output in R because by now you're all very good at reading Stata output if you need to. So we have this variance component here, 136 and some change, and the residual is 23. And the interclass correlation from those 2 numbers is 0.85, and I've got a reminder out here as to how that is computed. So it's the level 2 random intercept variance divided by that plus the level 1 residual. So according to this model, the denominator is the total variability in information test. So all the variance in one pile is what the denominator represents. The numerator is how much of that is level 2, how much of that is cross-sectional, how much of that is due to between-person mean differences. You can think of those things, any of those words. So 0.85 tells me what?
It's the percentage of between person differences.
Yep.
Yep. And which this is for level
2.
Level 2.
Yep. Is that a lot?
Yes.
Yes, it is. Yes. So For those of you who are doing power analyses or things like that for longitudinal data, if you use examples that are meant for clustered data in which the interclass correlation is like only 0.05 or 0.10 or things like that, like this is not going to work for that. So you get a lot stronger interclass correlations in longitudinal and repeated measures data than you do in other multi-level sampling games. So even for that, this is extreme. So this is reflecting the fact that this is a measure that's not really supposed to change over time. Like if it does, something went wrong with you, is the idea here. And is 0.85 significantly greater than 0? I don't need a significance test for this. Yeah, odds are good. So here's the likelihood ratio test against the model that has no random intercept variance, unsurprisingly, highly significant. So we know that there is a significant, very strong correlation of the occasions within a person. That's what we know so far. Now, a 3-level model. So the notation here, as introduced last time, let me zoom in so I can spend a little bit of time on this. The difference in 3-level notation is the use of 2 different sets of placeholders. So the first placeholder is beta 0. So this is how each individual person gets their own intercept. So C is for cluster here, for the family of twin pairs. Then the level 2 intercept is a function of a level 3 placeholder. So delta OOC is not a parameter. It is a holder for the parameters at level 3. So if we start at level 3, this is how each twin pair or each family gets its own intercept. It starts with the mean of the pair means. That's my gamma OOO fixed intercept. Then we get the V that I accidentally reused for my level 3 random intercept. So this would be like if you're from a family that knows more on average than other families, your V is positive. If your family knows less on average relative to other families, your V is negative. Those things fill out delta, come down here, then we pick up U. So U is not just between person anymore. It is specifically between people from the same family, which is kind of weird when you think about a family average for only 2 people. It's more like, do you know more than your twin, is basically what that means too. And for families in which there's only one twin represented, you want to guess as to whether that information goes to U or V? If I only have one twin in a family? 50-50 shot. Oh, guesses for V? Anyone want to guess U? Lots of abstainers. You're going to guess U? Way to be the contrarian there. Someone's got to do it. It is actually V. So if you only have one person per family, you cannot differentiate within and from between family variants. It goes up to the highest level. So people sometimes ask me, can I include clusters that only have one person or people that only have one occasion? You can, but that can somewhat bias the estimates of your variances at the higher level because that information goes to the top. So if I just have one person per family, they contribute to V and they don't contribute to U. So U differentiates the twins within a pair, feeds into the beta placeholder. That comes down to level 1, and then E is the difference between the twin-specific mean and that outcome for that occasion. That's E. So because these are 3 different levels, we can add these up and come up with the total still. They're orthogonal. So any questions on that as an idea? Okay. So now how to do it. This is something where you need to read your documentation and understand what it is assuming for you. So in Stata, the syntax must be written in this order where level 3 is first and level 2 is second. It thinks that's what you're doing. And if you try to do it in the opposite order, it will not understand or yell at you. So pair ID is a twin pair level identifier where both people from the same family would have the same number. Twin ID is literally 1 or 2. It is an arbitrary assignment of twins to a family. So the only way that twin ID being 1 or 2 would make sense is if the program understands that each instance of 1 or 2 is a unique instance when paired with pair ID. So in the corresponding SAS code for this, The level 2 identifier I have is pair ID star twin ID, meaning it's the combination of the two that differentiates each individual person. So 1 and 2 is sufficient if you're working in software that allows you to do that. It may not be. So bar pair ID with nothing after it means that I'm estimating a random intercept at level 3 because that's a default in Stata. Bar twin ID with nothing after it means I have a level 2 random intercept, also a default. And I'm asking for REML and Satterthwaite degrees of freedom. I'm asking for an interclass correlation, and I'm also asking for a likelihood ratio test against the 2-level model to see if adding the level 3 helps. In R, I had to figure this out. I'm sure there's multiple ways to do it, but here's the way that I found that I liked the best because it was the most explicit. I have 2 sets of parentheses. Pair ID gets a 1 for its random intercept. And then I have pair ID colon twin ID. It understood that as being level 2. So I have a 1 there as well. And I ask for an interclass correlation and another likelihood ratio test for that. So here is the corresponding output. Now I've got 3 distinct piles of variance. Cough, cough, homework question. How many pseudo R-squares could I possibly have then? If I have 3 piles of variance? How many pseudo R-squares could potentially be relevant for this model? 3. Yeah, I'm not trying to trick you, I swear. It's 3. And if you don't want to say pile of variance, how do you say that more technically, nicely?
Component.
Yeah, variance component, that would work. So 2 of them are random intercept variances, and 1 is a residual variance. So the first one it lists is level 2. So this is the variability of twins from the same pair, differences of the 2 people. Pair ID is variability across pairs, and residual is time-specific within-person variability. So we can sum all of those to come up with the total amount of variability and compute how much is at each level. So note the interclass correlation coefficient that R spits out is exactly the same number as last time. It isn't smart enough to anticipate that I want more than 1. So I did some math. Here is the table that summarizes the likelihood ratio tests. So the first one here is, hey, what if we dropped this term? That's the random intercept at level 3. Bad things. Hey, what if we drop this term? Also bad things. So this looks like we need a 3-level model, but these are significance tests, not effect sizes. To get to effect sizes then comes into different versions of interclass correlation and what they mean. So step 1 here, which I would always do for your reader, is to compute the proportion of variance at each level relative to the grand total across the 3. So I did that, and 54% is due to what family you're from. 31% is due to you versus your twin, and about 15% is due to which occasion it is. So those numbers, I used the original numbers, or you could shortcut it with the proportions if you want. Then I computed a couple different interclass correlations. The first one is ICC level 2, which is the amount of level 3 variability plus level 2 variability over the total. And this number is 0.851, which I noted is the same as before. Is this a consequence or a coincidence? Vladimir, when I ask this question, what's the answer always?
Consequence.
It's always consequence. Why is this a consequence? How does my 3-level model differ from my 2-level model, such that it would give me the exact same interclass correlation? What's the difference between 3 and 2?
Clusters.
Clusters. Which variance component is being pulled apart to create a cluster level variance?
Level 2 random intercept variance.
Level 2 is. So this intraclass correlation is functionally the same thing that we had on the previous page before these two were split apart. So yeah, it should be pretty much the same as what you get from a two-level model, because this is judging how much of the variability is at level 2 or higher. How much of the variability is cross-sectional is still 85%. That hasn't changed, because the purpose of the three-level model is not to split time varying from time invariant. It's to take the between person part and say how much of what we're calling person is actually twin pair instead of person. So this is between person in the numerator and total in the denominator, where between person now is partly between family and within family. So this is not new information. This is still the proportion that is due to person mean differences, and people are nested in families. The new one is right here, and this is one that none of the software packages will do for you by default. But I would argue that it is the more useful version in this type of sampling design. What I'm focusing on is a further decomposition of the numerator, of what we called between person cross-sectional. How much of that is due to which twin pair you're from? So then the numerator for that is the level 3 random intercept variance divided by level 3 plus level 2 as the denominator. So time's gone. We've already figured out the time part. Time is 15%, people is 85%. Now we're focusing on people. How much of the 85% is actually family, not person? And the answer, about 64%. So 64% of the 85% is how I would talk about this. And I have that written down right here. So of the total outcome variation, 85% is between persons and 15% is within. Of the 85% that's between persons, 64% is between pairs. So this ICC of 0.64 is the expected correlation of people from the same family. It is the effect size that corresponds to the significance test of whether we need a three-level model. So the likelihood ratio test said, yeah, we need a level 3 random intercept. This is how much we need it. 64% we need it. So if you give your reader these percentages over here, they can reconstruct any version of the ICC they want. So that's why I like starting with this, and then you can compute proportions for them if you want to. But these are the two that I think are most useful in this particular design. Okay, questions or any of that you want me to say again?
So like how, so if we were to do like a pseudo R-squared going from just the level 2 model to the level 2 to level 3 model, like we're computing the amount of variance that changes.
Mm-hmm.
Is that going to be like really the pseudo R-squared? Is that going to be really similar to this ICC level 3.6?
So the question was, would we do this process to compute a pseudo R-square?
Well, like would the value be very similar?
If you're willing to compute R-squares for new random things, then yes. But I will continue to die on that hill that doesn't make sense. So I would not use the term R-square in this context to describe partitioning a variance into levels. I would use it if we start to enter fixed effects per level to talk about how much of the level 3 did we get, how much of the level 2 did we get, how much of the level 1 did we get.
Got it.
Yeah. I brought up R-square, pseudo R-square earlier as a tie-in to your homework, where I'm asking, one of the questions was, what's the difference between pseudo R-square and total R-square? Pseudo is pile specific. But the idea that we have set up the fact that we need 3 piles then dictates that there are 3 different pseudo R-squares at a minimum that we'd keep track of. Okay, other questions, comments? So then what do other software packages give you? This is what both M+ and Stata give you when you ask for intra-class correlation. It gives you the level 2 one. Here's the 85%, but then it gives you pair ID of 50.54. What's that? That is just the proportion of variance at level 3. That's not really anything. If you want to interpret it in terms of correlation, this would be 0.54 is the proportion of variability at level 3. That would be the expected correlation of occasions from the same pair, not necessarily the same person. And I don't know why you'd want to know that. .85 is the correlation of occasions from the same person. The ICC that I did up here, 0.64, is the correlation of twins from the same pair. So this is something to watch for when you read papers and they report ICCs. If they don't specify what kind, you may not be on the same page with respect to what they're telling you. But this is what M+ gives you, and this is what Stata gives you, is what I call level 3B, correlation of occasions from the same pair. So in terms of where the action is, pair is the biggest thing here. This is a variable that is relatively constant, not only over time, but consistent within a pair. And if you think about the idea that crystallized intelligence and how much you know about the world probably has a lot to do with your educational opportunities and experiences, people who are twins probably had similar experiences. So it makes sense in the context of the design and the outcome. But there's still, within pair variability, a significant amount. Okay. So how about time? I first want to check at what levels I need to worry about time. Because any predictor, a logical precursor for specifying its fixed effects at a given level, is figuring out at what levels it even has variance. It has to have variance at a level before it can predict at that level. So I'm taking time-varying age, and I'm pretending it's an outcome. And I'm fitting a 3-level model to it. Syntax is the same. Here's the output. Level 2 variance in age, 0. And R got mad at me. My boundary is singular, fit, bad, no like. See help is singular. Convergence code, 0. Okay. Does that mean okay? Whatever convergence code 0 okay means, that does not make any sense. So level 2 variance in age is 0. Level 3 variance in age is 64% of it, and level 1 variance in age is 36%. Is this surprising? What do you think?
No, because they're twins.
They're twins, right? Like the definition of being a twin is that you're the same age. At most, maybe you're a day older because like one was born at 11:59 and the other was born at 12:01 or something, but like they're twins, right? Now, where this could show up is if they're still twins, but they were not tested together. Like if you started one twin 6 months ahead of the next one, then they're not the same age with respect to their participation in the study. But one of the things they were careful about in this study is to get them as close together as possible to eliminate that problem. So what this tells me is that when it comes to specifying the effective age, I have it at level 1 here, which would be what I would call time, right? Like how much older are you now than when you walked in the door? That was the point of doing a longitudinal design, to examine that. At level 3, some pairs are older than other pairs. That's cross-sectional age differences. So I have a fairly clear demarcation of age cross-sectionally as pair-to-pair differences versus age longitudinally as differences relative to when you started. So because of this pattern, that is why I set up my predictors the way that I did. So I first generated a new variable that is pair age at wave 1, which is the mean of the two at wave 1. So there should be very little variability across the two, but I wanted to make sure that it was purely level 3. And I centered that at 85, which was near the mean age at the beginning of the study. I'm not representing age at level 2 because it doesn't have any variance at level 2. And whatever tiny differences there are as a function of when the twins were actually tested are probably not enough to keep track of. Instead, what I'm doing is time in study, which is age minus age at wave 1. So this is how much older are you than you started, and then these are differences in how old you were when you started. And then I had to make time squared in order to look at quadratic random effects in Stata. Another thing that I did is center zygosity, such that MZs were the reference at 0 and DZs are the alternative group, because I'm going to put that in one of my models. And our code to do the same thing, I'm using Jonathan's function, add unit means. It works just fine if you list a data set to send the function results to and a data set here. It doesn't have to be the same data set. But where folks, I helped troubleshoot using this function is when they just ran this part without sending it anywhere, then it just like printed a bunch of crap to the window that didn't help. So otherwise, the code looks pretty much the same as anything that we would have seen. All right, any questions on that so far? So we got level 3 age, level 1 age, and I'm going to put them both in at the same time. Why does it not want to go there? I don't know. I'm not going to fight with Word. I'm just not. There we go. We'll go to age. Next step. So this is sort of a review of the process of unconditional modeling. What kind of trajectory am I going to fit? I don't know. I'm going to need to make a picture. So I fit a saturated means model with random intercepts at level 2 and level 3. So wave is the categorical rounded version of time. And I treated that as a categorical predictor in Stata via IDOT, asked for margins and then a picture. And in R, I did the same thing in a cheaty way by turning off the general intercept and then saying as factor wave. What that does is rather than specifying wave mean differences relative to a reference wave intercept, it just spits out the means. So it just saves a step in terms of getting the output. So here's the output for the means of this outcome over time. And this is wave, which is every 2 years. So each of these intervals is not a 1-year interval, it's 2, but the shape is the same. Looks sort of bendy to me. I'm going to go like quadratic bendy. Seems like a reasonable thing. So that's what I did. So here are, let's see, first just the fixed quadratic time random intercepts. So I have age TIC minus age 1 IC. So subscripts at this point are critically important to describe what a variable is varying over. If you only have one level, you can skip the subscripts. You have 2 levels, probably need them. 3 levels, you definitely do. Another thing that I'm doing to help future Lisa understand this notation, labels. So there's nothing that prevents you from clearly defining what each equation is there for and what it is doing. Future self will thank you if you do this. Because like gamma 1O versus O1 versus this versus that, like this is a working memory overload. So I've got beta 1, which is going to be my linear slope. Beta 2 is my quadratic. Because I have 3 beta placeholders at level 1, I have 3 level 2 equations. That part's the same. The difference is that each of these, rather than starting with its fixed effects, starts with another placeholder for what's going to happen at level 3. Because I have 3 level 2 placeholders, I have 3 level 3 equations. Now the fixed effects show up. So I've got OOO because I have OOC, and this one is OOC, so it all matches. So then this is the fixed intercept, this is the fixed linear effective time, fixed quadratic effective time. This is my level 3 random intercept with the V, my level 2 random intercept with the U, and then E is over here. Okay, Nathan, question.
So I hope this isn't a stupid question, but the first subscript for the betas, where it's
Yes.
like, is that referring to time, or is that just saying this is beta, like this is the first beta parameter that we're estimating?
Both. Beta keeps track of which effective time you're on, and we can't start counting at 0.
Okay. And so for beta 2, why isn't it beta TIC?
Because we're filling in the 0s, 1s, and 2s with respect to the order and predicting time.
Okay.
So the numbers take over the subscripts once you get into prediction. So like OOC is because it's beta 0, but it's also the first term in predicting beta 0. This is 10 because it's beta 1, but it's the first term. And this is the predicting beta 2, but it's the first term.
Okay, so when we get into like the level, like the sub-equations and the levels, then on the right-hand side, the subscripts don't have, I don't want to say arbitrary, but they don't have like time-related meanings. Is that what you're saying?
I think so. So the fact that this is the betas, they control what's happening in the level 1 model, and the order of their numbers is which term in the level 1 model. The same applies for the second subscript with respect to the deltas, and then the same applies for the last subscript is what's happening at level 3.
Okay, I think I understand.
Okay.
Thank you.
Yes, and again, that's not a stupid question. I'll remind you, it took me at least 10 years to figure out how to do this correctly. This is non-trivial in terms of complexity. This is just a simple model, right? Relatively speaking, this is a fixed quadratic random intercept model. So we have, there's my fixed quadratic, my fixed linear terms, my 2 random intercepts, same as usual in terms of that. So we have 2 random intercepts still. I've got my level 2 random intercept and my level 3 random intercept and my time-specific residual. Which of those 3 should time have explained? This is a pseudo R-square question.
Level 1?
Level 1. The answer is always the one in its equation. These terms are explaining E. You have to like Jenga your way up to level 3 to find them, but once you work through the substitutions, then the fixed effects are right here. So here are my 2 fixed effects. Let me zoom in a little bit so you can see that. So my fixed intercept is 26. That's my predicted information test outcome at time 0, which is when they walked in the door. What kind of curve is being created by my linear and quadratic slopes here that are both negative? I will take gestures or words for this. Yeah, sorry, Zoomers, I'm backwards for you. I think it's this way. Yeah, it's like bendy falling off cliffy. Yeah, this. Now it looks like a heart. I love being a dork. So what I would say is that at time 0, there is significant linear change of minus 0.32 per year. That change becomes more negative, speeds up by how much? And don't say 0.03. You could do it.
Twice?
Twice, yes, twice the quadratic. See, this is like the greatest hits collection of this class, right? We're revisiting all the old hits. This is the twice the quadratic is how the linear slope changes per unit time. Now note, it's not significant. For now. Da, da, da. And at this point, I got lazy and said, I'm just going to paste in some SAS output that gives me the pseudo R-squares because I don't want to do the math in Excel. So forgive me for that. But I have routines that do these things. So here's the empty model variance components. Here's my fixed quad variance components. And as we had predicted, it's the level 1 variance that goes down. So time and time squared explained 8.3% of the variance. The fact that the residual variance is lower necessarily means that the random intercept variance goes up. They are tied together in terms of how they are estimated. The random intercept variance is not just person mean differences. It is corrected for the expected contribution of chance, and chance is residual variance divided by the number of observations at level 1. So every time residual variance at level 1 goes down, level 2 variance goes up a little bit to compensate. Doesn't mean I screwed it up, it's just a necessary consequence. So next question then. Do you think people need their own rates of change? I don't know. Let's find out. And because I knew that we would be at this point in the semester, I'm like, here, this one. I'm not even going to make you find it. It's U1IC. There's a joke in there somewhere, but I'm too weak for it. So it's U1 because it's beta 1. It's IC because it's per individual per cluster. And it goes in the level 2 model because these are differences between people. So just one random linear time slope right now at a time. I'm not doing anything to level 3 yet. So in terms of the code, Stata users note that I not only added a random time slope, but also this term right here, covariance unstructured. That means my G matrix gets to be whatever it wants. That means I need covariances between the random effects from the same person at level 2. That happens by default in Elmer, so you don't have to worry about that. So in Elmer, I've got 1 plus time here in the level 2 section of my parentheses. I also saw versions of the model that had things that were like slashes like this, and I couldn't figure out how to make it so that you had different random effects at each level. So then I discovered you didn't have to do the slashy thing, and I just did it this way. So this may be slightly more code than you need, but I think the transparency makes it worthwhile. So just the time random slope at level 2 there. So here we are. Zooming in so you can see, we do now have a random time slope with a variance of 1.5. It has a correlation with the random intercept from level 2 people of 0.19. So note there's only one correlation because you're only allowing correlations between the random effects at the same level, not across levels. So where you start and how fast you change is positively correlated in this case. However, keep in mind that these are decreases. So that means that people who started out higher, if it's a positive correlation, have a high slope, which means a less negative change in this context. Like if you picture the distribution of down slopes, like less down is what high means, not growth. So it gets tricky to interpret intercept slope relationships. We have to know which way the slopes are going in order to think about what being high on the variable is versus low. A high slope here means less negative. And there's no p-value. How do I find out if this is significant? See, greatest hits. How do I test if I need a random anything? There it is, likelihood ratio test. In M+, it gives you p-values. Not supposed to look at them, though. Here's my likelihood ratio test. Survey says difference in model fit of 136, so yeah, I think so. And note, my fixed quadratic effective time is now significant. What? Charlotte, you're nodding like I saw that coming. It's cool, but why? Think about the piles. Where'd the random slope variance come from? Level 1 residual. So level 1 residual variance is smaller, not because it's been explained, but because it's been partitioned. But level 1 residual is the numerator of these standard errors for all intents and purposes. So less error as a point of comparison means that your effects may be more significant than they were before. I kept in fixed quadratic because it looked like I needed it based on my bendy line. All right, so keeping my random linear time slope at level 2 because it helped the model. I'm going to add one at level 3 now, and again, here it is, V1OC. So now the random effects are parallel in structure. I've got an intercept at level 2 and level 3. I've got a random linear time slope at level 2 and level 3. So what question am I asking by adding this term here? What is this going to tell me if it helps?
If the level 1 time slope differs between groups?
If it differs between groups, I will accept that as an answer. Can someone say the same thing in a different way?
If the rate of change between groups is constant, or this allows it to not be constant.
It allows the rate of change across groups to not be constant. That is also true. Ask if pairs of twins differ from one another. How about relative to what what the model would gain relative to having it at level 2 only? How about shared variance? In the same way that we talked about moving from a 2-level to a 3-level model, as, okay, this is between person, how much of between person is really between family? Same. People need different slopes, but how much of the fact that they need different slopes is family, not just people? In other words, is there a commonality of the change between two people from the same family? A dependency, if you will. Yeah, go ahead.
Is this what you were talking about on Tuesday, where when you're asking about redundancy, because why would you have a separate variance term for a group and then also people within the group?
Yes.
Okay.
This, because it's not redundant, it is a partition. What we are doing is saying how much of what we called U1 actually is V1. The picture that it goes with is this one. Let me go through this real quick. This is slide 14 in lecture 6. So this is the empty model partitioning of variance. Once upon a time there was an E. We split it into time and person. Then we take level 2 person and split it into between and within families. Then we put fixed effects of time in, and then we split the residual out into what is within person variation over time versus between person differences in change. That's what we're at. Now this one splits. How much of what we were calling between person variance and change is actually between clusters and within clusters? It is the exact same set of ideas, just with respect to change as the thing we're talking about and not means. That's where we're at. So now I have time in both places, and covariance unstructured in both. That is not redundant. You have to type it twice, because it's dealing with each chunk of the G matrix specifically and whether there's a covariance allowed between random effects at that level. I'm asking for what the correlation is at each level. So this is a way to do that, what I call G-core. Likelihood ratio tests to judge the contribution of the random linear time slope at level 3. In R, it looks the same, except for now I have a parallel structure of 1 plus time in each part of the randoms there. And now we have a parallel structure across levels with respect to intercept and linear change. So at both levels, the intercept variance is now specific to time 0. I have time variance at level 2 that is 1.45, so it's smaller than what it used to be because it's been split. The new term is right here. Time variance at level 3 of only 0.10. So I've got all the words out here. This is not R, this is me being nice. I once had a student ask me that, like, my version of SAS doesn't have the interpretations in the last column. Like, yeah, no shit. Like, this is why I have a job. There is no version of SAS that does the interpretations in the last column. But you know what? There could be. There could be, right? And think how popular that software would be if it interpreted things for you. Because it's algorithmic. So, higher goals, but not today. So do we need it? Survey says Feel free to read from the screen. We do not need it. It did not help. So that is a significance test. Let's go with effect size. We're going to take our friend interclass correlation and do it a different way. So now, specifically focusing on the intercept and specifically focusing on linear time slope variance, I have an interclass correlation of 3 versus 2 and 3. So the numerator is the level 3 term, in each case, intercept and linear time slope variance. The denominator is level 3 plus level 2 of the corresponding terms. So the new information then is this right here. The way I would talk about that is of the total variability between people in change over time, only about 7% of that has to do with what family you come from. So are two people from the same pair changing similarly? Not really. Said differently, the average correlation of the linear slopes from the same family, only 0.07. Very tiny correlation, not significantly different than 0, according to my likelihood ratio test. In contrast, if I break down the intercept variance specifically, of the total between person differences at time 0, 64% of that has to do with what family you come from. So there is a very strong correlation in the amount of knowledge between twins. There is a weak correlation in the change in knowledge between twins. So my guess is that the geneticists are not very happy with this result because it looks like people don't change the same. But if you think about what causes change, there may be some genetic components to diseases like Alzheimer's disease or other types of things that would cause change, but it's not lockstep with your genetics. There's a lot of individual factors that would contribute to that. However, even though we don't need this, I'm going to keep it. The reason is because where I wanted to go with this example, which this particular group of students may not care about, but the last time I did this, they did care, was to do a genetic decomposition of the extent to which there are MZ and DZ differences in the size of the correlation. If MZ twins share, help me with this, like more genes? I forget how to describe it. Can anyone help me? Please don't make me the geneticist in this room today. I'm not prepared for that.
Isn't MZ like one? MZ is one that splits, yeah. And DZ is like your two.
That's right.
DZ is like your like sibling. So just share an allele. Mono is like you start out as like one little blob.
Yes, monozygotic is one egg that splits. Yeah. Dizygotic is two eggs that just chill out together and then show up at the same time. Okay, got it. So in theory, you would expect the interclass correlation to be stronger for MZ twins than DZ twins, if there's a genetic component, right? And then by that extension, like if you did family research, like you could look at sort of full siblings versus half siblings and like break it down into that. And I've seen research focusing on that. But twice the difference of interclass correlation is how you compute heritability, because everything really is a multi-level model. So at this point, I'll spare you the details of testing random quadratic slopes. Nope, big nope, broke the model. So we're going to go with random linear, keeping the level 3 random slope variance because it isn't causing any problems, and I'll need it for later. So now baseline age as a predictor of pair intercept and change. So this is a level 3 predictor that I've added here in 3 places. So I have 001 because pair age is the first predictor of the intercept. I have 101 because pair age is the first predictor of the linear time slope, and 201 because it's the first predictor of the quadratic time slope. Note that I don't have a V here at the end of the quadratic time equation, and I don't have one here either because I don't have random effects. So what would I call the quadratic time slope then, given that it's moderated by something, but it doesn't have a random effect otherwise? 2-word phrase, first word starts with an S, second word starts with a V. If it ain't fixed and it ain't random, What's the happy medium?
Systematically varying.
That's it, systematically varying. So what we're saying is that you need a different quadratic term to describe your trajectory as a function of how old you were when you walked in the door, but it doesn't vary randomly across people or pairs otherwise. So then here's my 3 new moderators. Here are my 3 new moderators in R. And of course, one more multivariate wald test just for old time's sake. If I want to answer the question, do trajectories differ by age? Trajectory is 3 things, right? Intercept, linear, quadratic. So I can make a hypothesis test that asks, does age moderate the intercept? Does it moderate the linear? Does it moderate the quadratic? And I can do the same thing more painfully in R as well. Survey says, does age moderate, hey, come back here. Does age moderate the intercept? How so? Negative number here. Explain it to me like I'm 5 years old. How does age moderate the intercept?
As age increases past 85, the intercept decreases for every year past 85, or whatever unit it's being measured in. The intercept decreases by 0.876.
What does the intercept refer to specifically?
Time 0, age 85. I think that's it.
Yeah, time 0, meaning when you walk in the door. So yes, for every year older you are when you walk in the door, you and your twin pair, you do worse at time 0 by 0.87 per year of age. And just for old time's sake, what do the interaction terms do to the linear and quadratic slopes, even though they're not significant? 4 choices.
More negative.
More negative, yes, unquestionably. Go down morer. Older people go down morer. How's that? Does age moderate the trajectory? The hypothesis test lumping the 3 slopes together says sure, except when you dig into it, not so much the trajectory, just the starting point. And which variance component should the main effect of age have predicted?
Level 3.
Level 3, which one? There's 2.
Random intercept variance.
Intercept, yeah, because this is a main effect. How about time by age?
That's the
You got 5 choices.
level 3 random variance of our level 1 slope.
Yep, the level 3 random variance of level 1 time. V10. Yep. How about the last one? Quadratic time by pair age.
Residual variance.
Yeah, residual variance. Why?
Because we don't have random effects for that slope.
Yep, because we don't have anything in its row. So going back up here and answering the same question, which variance component does the main effective pair age predict? The one that's in its row. That's my random intercept at level 3. This one right here, gamma 101, that's age by time. It predicts that one. This one, 201, age by time squared. Wow, no, I don't have anything. I gotta jangle my way back. I don't have anything here either. Oh no. There's E. I'm a little loopy today. But yeah, there's nothing here, and there's nothing here. It's got to be here. Just got to kind of follow your way down there. All right. What else is in here? Oh yeah, here's the actual R-squares. So 8% of the level 3 random intercept by the main effective age. Now this one's surprising, or is it? I got 39% of the random linear slope variance at level 3. That's a lot, right? How much was there to begin with? A non-significant amount. I got 39% of nothing. Or next to nothing, I should say. So it's 7% of what was at level 2. So this is 39% of the 7% that was at level 2. And the residual actually went up, highlighting why pseudo-R-square is called that. Last but not least, zygosity as a moderator of everything. So MZ versus DZ as a main effect and as an interaction with age, moderating everything. 6 new terms here. Does the trajectory, as defined by time and age, differ by zygosity? That takes 6 slopes to answer that question. And this painful thing in R. But just look at this thing. Like, if this was you a year ago, like, you've been like, what is that? And now you're like, I know what this is. Do you know what the hardest part of figuring this out was for me? It reordered my stuff. I wanted to put it in the order in which I had wrote it, and I was like, no, main effects first, damn it. Okay, fine. So I had to reorder it, and then this worked. So here's my big old list of fixed effects. Here are the new ones, and that one. Survey says, looks like a whole lot of nothing. Now, is that surprising? That zygosity does not matter? Not surprising? We got some head shakers. Why not?
I would expect more of the shared variance within twin pairs to be due to kind of environmental effects as opposed to health.
And what are these? Are fixed effects, right? What are they doing? Are they talking about shared variance? No, these are adjusting the predictions. So the main effect of is DZ, for instance, which actually is technically significant, but this I would probably call a type 1 error given how much stuff is in my model at this point. That means that people who came from 2 eggs score slightly lower at time 0. Like that, why would that matter, right? So no, this whole exercise was designed as a precursor for the thing that I wanted to do, which was to figure out whether or not you needed heterogeneous variances by zygosity. And I tried very hard to make this work in Stata and in R, and I couldn't, so I give up. If anyone wants to figure it out, go for it. I gave my best try in the syntax files online. Because in SAS proc mixed, all you have to do is say group equals zygosity, the end. And you're allowed to have separate G matrices at level 2, level 3, and R matrices at level 1 by group. So then, as usual, anytime you mess about with the random part of the model, that's a likelihood ratio test. So I did that, and I end up with this big list of variance components, where you can tell the level 3 stuff, also because I labeled these for you. This is the column that SAS does not provide. Here's the level 2 stuff. And notice this thing right here. There is no common change variance in DZ twins. However, there is common change variance in MZ twins. So the shared variance idea actually does appear to hold up. There is a stronger correlation of change within twins that are more genetically related than others. So then you can go through the math, which I did, to decompose how much of that variability is due to level 3, what is called the A part, heritability, common environment versus error. And for the intercept, it looks like a whole lot is due to heredity. For the slope, a whole lot is due to heredity. However, I have a variance proportion of minus 32%. And yes, that can happen, because the way that these are computed is twice the difference in interclass correlation. And then this is what the remainder is. So, and here's some words. Ta-da. In the few moments that we have left, I want to give you some big picture stuff. Remember smushing? If I have a level 1 predictor, how many predictors do I really have in a 3-level model? 3. If I have a level 2 predictor, how many predictors do I really have? 2. So yeah, everything you learned about smushing still holds. Here's some examples in the slides that you can look at on your own. This is coming straight out of chapter 11. Variable centering. So for instance, if I add a predictor of time varying stress, I would center that at person mean stress to get a purely level 1 version. I would take person mean stress and center it at family mean stress to get a purely level 2 version, and then family mean stress minus some constant to get a purely level 3 version. And now you know why I call this variable centering, because this is both person mean centering and family mean centering at the same time. If you wanted to do constant centering instead, then what you get at level 2 and level 3, can you guess what they'd be? Or read from the slide, your choice. Yeah, everything's contextual. So then you get the pure effect of level 1. This is how the level 1 differs from level 2. This is how the level 3 differs from level 2. So these hurt in this way of speaking. This is only applicable if you have time-varying predictors that don't change over time. If time-varying predictors themselves change over time, do you get to do this? You do not. What do you get to do instead? Multivariate, 3-level model. I know. What about interaction terms? They go in at all the levels too. So if you want to test moderation, that's 3 interaction terms if your variable is measured at level 1 and all that stuff. Here's pseudo R-square and what predicts what, roughly speaking. And yeah, I think that's about all I wanted to say. Oh, one more thing. What happens if your groups change over time? Can you do it this way? You know, what if your groups change over time? Do you just ignore it? Or can you model it? You can model it. You can always model it. That's always the answer. So the idea of time-varying groups are what is known in the education literature as value-added models, where you're trying to pull apart the unique combination of the teacher and the kid and the occasion. The way that I would approach this, I have a bonus example posted on the website from a couple years ago. The key idea, let me make this a little bigger, this is slide 20, is to build custom intercepts that control when someone was in what group. So the way that I would approach this, here's a stacked data set. Let's say that I have 3 occasions potentially. Let's look at kid 102 here. The first time they were in class 3, the second time they were in class 21, and the third time they were in class 42. So there's 2 ways that I can look at the dependency of kids from the same class. One is that it's temporary. So I call this acute. So what I would do is build separate predictor variable columns that work like switches for whether you are applying the effect of that class in that year and not in the other years. So an intercept is just a column of 1s. This is a column of 0s and 1s to control when the intercept kicks on and off. Another way to think about it is that the dependency stays with you. If you have a really good kindergarten teacher and you learn how to read, that boost may show up in 1st grade and in 2nd grade. So from that perspective, I would build columns of 1s that continue so that the effect of being in a year 0 classroom shows up in year 1 and in year 2 as well. And this is what the code would look like to do that. So this is the second half of chapter 11. So this is a crossed model in which occasions are nested within children, occasions are nested within groups, and groups and children would be crossed at level 2. You can set this up as a fixed effect or as a random effect, and there's example code on the book's website to do all of that. There. How's that? And I still didn't get through everything, but they won't let me have a 3rd semester of this. They cut me off at 2. All right, any questions on any of this stuff that I just breezed through quickly? But it's all in the book, chapter 11. No. All right, then, with the 4 minutes that I have left, I want to issue a very sincere thank you to each and every one of you for sticking with me for this whole journey. I'm very proud of all of you. I was really impressed by your presentations, and I hope that I get to see you do some cool shit in the future using these models and all the other things that you know how to do. You have earned the right to bother me going forward, right? Because you've been through this process. So if you have questions in the future, if there's things that I can help you find in terms of resources or advice, I'm happy to do so. Deal? All right, then that's it. Office hours next week if you need me. If you don't, have a great summer. Yay, can we clap it out for everyone? Yay, everybody. Thanks for being here. Bye, Zoomers. Bye, Roomers. That's the end.